Okay. Hey. Okay. All right. We're gonna go through the vocab here. It's at a total of 69 points. The practice guide is almost the exact same. But let's go through the scores here. Let's go through like what the answers were, in case you didn't know. Again, you always have the option of retaking. You just come in the morning, 10 minutes, or after school, it can be either or. Minimum 10 minutes with me, and then you can retake. We'll go over the problems you missed, and we'll try to get a date set for you, but it's got to be within the next week if you choose to retake. I didn't have anyone fail, so that's good. So it's just one of those things like, if you're not comfortable with your score, you always have the option of retaking it. But let's go through these again. I left everything on the board so I can compare and I can point at it. But let's kind of walk through this here. All right, first one, a quad. So it's got to be a four-sided figure, has opposite sides parallel, so it can either be a parallelogram, rectangle, rhombus, or square. And it has four right angles, that's automatically a rectangle. That's the one shape that has that definition. Intersection of two geometric objects that form right angles, that's the word perpendicular. That word, that definition has been on every single chapter test we've had up till now. Every single one. Angles, on the inside is interior angles. I don't believe anyone missed that one, that was pretty easy. A segment that contains two non-adjacent vertices that pass through the interior, that is the word diagonal. Now, the key word here, diagonal, what I want to talk about was, I had a lot of questions on Thursday, Friday, about that formula right there, the n minus 3 divided by 2. That formula is the number of diagonals inside of a shape. So, we didn't need it. It was one of those things, I put every formula that was in the chapter that you needed, I put them all up on the board. But that one I had a lot of questions on, like, Ward, I didn't even recognize that formula. It was the one day we were talking about how many diagonals there are in the shape. You take the number of walls times the number of walls minus 3 divided by 2. That was the diagonals, okay? Geometric figure that does not take cavity is a convex picture. Converse is a conditional statement where you flip the hypothesis conclusion around. The sides of a polygon is called an edge. Now we get into most of these theorems now. A quad, that's a parallelogram. Well, since this is a theorem that talks about parallelograms, there's only a select few numbers. If you can see the board over there, 6.3 to 6.8 are the formulas or the theorems about parallelograms. So, parallelogram, opposite angles are equal, that's 6.4. That theorem was also on the practice guide. It was the same word. Same actual spot, I never even moved it. Next one, quad, that's a parallelogram. The diagonals bisect each other, that's 6.7. Those are all of your theorems about parallelograms, right there, back to back. Next one, equilateral is a geometric figure with all sides equal. I had a lot of people trying to tell me rhombus here. The only reason why this isn't rhombus is because it didn't say it had to be a four-sided figure. It could be any geometric figure that has all sides equal. Okay? 624. Hey. Okay. Mid-segment of a trap is parallel to the base, and it measures half the sum of the bases. That's 624. That's the theorem about trapezoids. That one in particular, this theorem, is the one you have to use on problem number 9 on the back page. You have to use that idea that you add the base together, divide by 2, that gives you the mid-segment. We'll get to that one. A lot of people just do it with a shortcut. They don't even need the formula, which is kind of easy. I kind of showed you how that works, but if you didn't know that was the formula, that's why I put it on here in case you needed it. 6.2. The sum of the exterior has to be 360. That was 6.2. That's about any polygon. There's only 3 theorems about polygons that we've had. There was 6.1, which was the interior. We had exterior, which was that one. And then we had the polygon about the diagonals. So there you go. Rhombus. Now it's a quad. Opposite sides are parallel, and it has 4 equal sides. That's a rhombus, not equilateral. The reason being is it's actually a quad. It's more specific than just a regular equilateral object. Okay? 6.15. It's a theorem about rhombus. Well, the only theorems about rhombus is 6.15 to 6.19. You shouldn't get those wrong. There's only one of them on there. So it's a theorem about rhombuses where the diagonals are perpendicular to each other. If we keep going, we actually are going to use 6.16 later on in this. On this particular test. Okay. 6.15. A quad. One pair of opposite sides are parallel. The other pair are congruent. That's the definition of my isosceles trap. It's got equal walls. It's got a pair of parallel sides. Now, there's a reason why I put this one on the test, and there's a reason why I skipped the third section in your book. The third section on this chapter 6 had one particular theorem I did not want to cover. It was theorem 612. It talked about a quad with a pair of parallel sides and the same set of sides are equal, not the other pair. It was super close to this definition, and that theorem, the theorem 612, was about parallelograms, not trapezoids. And that was the whole reason why I skipped it, is because that definition looks way too close to that theorem. Like it's nearly word for word, except for a few, instead of saying the other pair, it says the same pair. So it's one word off. It's just, that's the reason why I skipped the third section. It was the only theorem I just didn't want to cover, and it didn't have a purpose for what we needed it for. Now let's keep going. Quad, that's a kite. Oh, there's only 2 theorems about kites. Kites, exactly one pair of opposite angles are equal. This theorem we're using on later on the test as well. You'll see that. And then a bisector is a line, ray, or segment that cuts an object in half. I had a couple people try to tell me that that was a mid-segment or other things. A bisector cuts things in half, and it can be any object. Okay? All right, there's your vocab. Pretty good scores on that. There's a few that were not so great, but again, all you had to do is kind of study. And I really told you what was going to be there. Like on practice test days, if you watch those videos, I was really telling you, like I told you explicitly, the word edge, equilateral, what theorems could potentially be there. I talked about rhombus and rectangles, interior angles. I was really telling you kind of what words you need to study. So those are things you need to catch when we're on practice test days.
I just write those down.
Yep. Okay, all right, next one. This bottom problem on the first page. The most commonly missed thing about this problem is that a lot of people didn't put the 540. They're putting a lot of 360s and 180s. The idea is that you're adding up the interior, you have to figure out what those add up to be. It's not always 360 on the inside. That's why we have this interior formula, which is on the board there. Okay, 180 times n minus 2. That tells you what the interior angle should have to be. There's 5 walls, I even counted them up. There's 5. Plug in 5 minus 2, which is 3. 3 times 180, that's 540. So all 5 of these angles should have to be 540. You can see my math that I'm adding. The most common mistake, other than getting the 540 wrong, a lot of people put 360, and I think you automatically missed a point on that. If you didn't have all the parts, you missed another point, because I know the common missed thing, if they got the 540 right, a lot of people missed an extra X. So you got to make sure you have all the objects when you go spin around the objects accounted for. You get to 74, and then you plug them back in. And yes, you did have to tell me exactly what each angle was. I warned you of that on the second day when we were doing the test. You have to explicitly tell me A is this, B is this. Some people didn't plug it in, you automatically missed points. The second or third commonly missed part about this question, I had a lot of people putting these two equal to each other. They don't have to be. In fact, they're not. The reason why I know that they're not, they're using the same 2x. You can't have the same 2x and adding a number and subtracting a number get the same angle. Because whatever x you plug in, there's no way you can add 10 to this and subtract 20 and get to the same number. It's not possible. It's an undefined problem. Because if they had different x's, like this one had a 3x, that one had a 2x, I could understand that that would work, but the way they have this set up doesn't. So you couldn't set those equal. Yeah, I think if you set those two equal, I think you automatically miss 3 points or more, depending on what your math was. Because some people that did that, they did really fishy math to try to prove something. All right, moving on. Number 2.
Math is fishy.
Adding up all the exteriors, you get 360. You can see all my math. I add them all up to get 360. 360 get really small. Subtract the 27 across, divide. The only missed thing I saw in that one, I saw a lot of 180s, not 360s. That is not a triangle. And the other thing was, I saw somebody didn't add all the x's together. They found an extra x, so they had 8x. So they got a weird decimal. But moving on, number 9.
So, no matter what, in the exterior angles, it's 360?
Yeah, that was the theorem 6.2. It even says it up above.
Oh, I did the...
Theorem 6.2, some of the exteriors should be 360.
I did the thing where it's 180 and minus 2, and I got like 720.
No, that's interior. Nope. Okay, alright. Hey, number 3.
At least it was only minus 1.
Yeah. Number 3, you set these equal, because opposite walls are equal in a parallelogram. It is a parallelogram. Set those equal. You can see my math there to solve for B. Set the A's equal to each other, so you can see what I solved there to get. Should be pretty easy. You can see all the steps I did there. Most people didn't miss those. The next ones, you're setting these diagonals equal to each other, the certain segments, because they are bisected. That was the theorem 6.7. That's why I put that theorem on the top, because these sticks bisect each other. That means it's the middle, so the sticks are equal. So you can see I set the z's equal to each other, I set the y's equal to each other, and I actually solve. I had some people like trying to do these crazy formulas where they're adding them up to make 360s and 180s. Those aren't angles. You can't do that, they're walls. Walls don't have to be any specific number like 360 or 180. 5. Let's see. Problem number 5, you just had to set the opposite walls are equal. Because it is still a parallelogram, so opposite walls are equal. I solved, set the opposite angles equal to each other. You can solve for that. Again, I had a lot of people trying to like make up numbers and try to solve. There's a couple different ways to find y, but I thought the easiest way was just setting the opposite angles equal. Okay. Next one. This one really threw some people for a loop even though it was supposed to be easy. The first thing you have to do is solve for y. These sticks are equal just like the problem up above. Set those equal, solve for y. Then you can take the 13 and plug it in here. 13 plus x is equal to the 16. Because I just plug the 13 back in. And then you solve for x. Like all you have to do is use the y to solve for it. Like it was meant to be like a super short problem. In fact, that problem's actually easier than the ones up above. So I had a lot of people like really messing with that problem. They thought it was supposed to be a system even though it's not.
Will you wait a second? They're all. Alright, never mind. I just don't want to keep going.
Alright, moving on. Number 7. Number 7. You had to set these equal to each other because on a rectangle all the diagonals are the same. I even had them marked. You set those equal, you solve for x, but then the problem was some people didn't go on. You had to solve for zx and plug it back in. When you plug this in, you have to plug it in for zp and then just double it. So when I plug it into zp, you can see what I did is I just added zp twice and then I plugged in my x. But if you just plugged it into the ZP and took it times 2, you got the same 38. I had a lot of people like trying to label the picture, but you had to solve for x and actually solve. Again, I had a lot of people like they're trying to add them up to make 180s and 360s.
Okay.
They're segments, they're not walls, or they're not angles anymore, so you can't add them to make 360. Okay, if they're walls. And how I know that they're walls, it's only 2 letters. That should be a dead giveaway. Number 8. These are angles. Now when you label the picture, ABC, that's this angle, BCD, that's this angle, they're not the same angle. You can actually see it from the picture. That's acute, this is obtuse. You can see it. So the only thing that you should know, since this is a rhombus, these angles have to add up to be 180. That was one of it's called consecutive angles, it's Theorem 6.5. The angles can add up to be 180 on the inside. I had some other people trying to do some other math. There were some other ways to do this problem, but the easiest way is just to add the 2 angles together, solve it out, because they add up to be 180, to get 46, and then what you have to do is you have to plug it back in, and this is where it gets tricky. You had to find DAB, or BAD, whatever you call it. That's this angle. The only way you can find this angle is plugging into that one, because it will transfer across. This angle is BCD, that was the 2x plus 3, so if I take my 46 and I plug it back in, you get 95, and that angle does look like it's obtuse, so it was drawn somewhat to scale. Okay. Number 9, that is a trapezoid. You could do it by the shortcut, very, very easy. The VS, the mid segment's 9, the UT is 12, so they went down by 3, go down by 3, it's 6. That was the shortcut I told everyone in class. You didn't even have to show work on that one. But if you did it with the formula, which is that Theorem 624 up above in that vocab, you could add the bases together, cut it in half, because half the sum of the bases is equal to the mid segment. So you add the 2 bases, divide by 2, multiply the 2 across, and then subtract the 12, you still get the same 6. I think most people just do it by the shortcut. Yep. The only problem that I saw that somebody missed this one was they put the 9 and the 12 in the wrong spot. They put the 9 up here, they put the 12, and then they were trying to find this number, and so they said, okay, 9, 12, they went up by 3, so they went up by 3, and they told me it was 15. Oh. Technically, they did their math right, they knew the shortcut, they just plugged their numbers in the wrong spot. Because it told me that VS was 9, so they're labeling the wrong locations. But yeah, that was pretty much the only thing that I saw somebody make a mistake on that one. That I can remember anyway. 10, this is the one that I said earlier, this kite problem, you had to know your Theorem 626. That was the one up in the vocab, where it said it has 1 pair of congruent angles. So on this picture, there's 1 pair of angles that are the same, it's the 85. It can actually transfer across. So the reason why I know that they're squeezed between the two walls that are marked the same. So that's why this angle over here is in between the same walls. They look like they're the same angle, and on a kite they are. The other two do not. That one looks really obtuse, this one doesn't. It actually looks like a cube. To solve, what should this add up to? Yeah, 360. It is a box. It's square. It's like a rectangle kind of thing. It's a kite, but it still should add up to be 360, so you're still doing interior. So you're still doing that 180 n minus 2 thing to get 360. And then you can solve for that angle. That's the one that's missing. That's the one that they wanted me to find. So if you see the math there that I'm doing, you're adding them up to make 360, and then I subtract it over and I get 70, and that's my angle C. The only common mistake that I saw somebody make is they thought they could just transfer both numbers across. Like the 120 goes across, the 85 goes across. That's if it was a parallelogram. Opposite angles are equal. That is not a parallelogram, so the opposite angles don't have to match. Okay, I'm going to walk around, I'm going to collect. Then what we're going to do today, I just want to intro what we're going into, and that's it. It's going to be super short. I'm going to hand out some paper. It'll be bare minimum notes, just the intro. That's all I want to do today. I don't want to do anything super complicated.